Alrighty. So this is going to be. So we're gonna be doing Physics 111, Chapter 6, which is gonna be force and motion. All right. Let's go ahead to our module. Chapter 6. All right. So chapter 6, force and motion, is from the last class. Now, we talked, actually, we touched a little bit about friction and frictional forces. So let's go ahead and look at these little videos that we have about the friction forces. So it's kind of like the air hockey table. When you have the air going in, you can actually play air hockey and the puck would go in on the table smoothly. Same thing with this one. So what it is, you're creating a frictionless surface by putting the air cushion on. So in real life, frictional forces are almost always present. Now, the direction of frictional force always opposes the motion. Now, sometimes friction is bad because it dissipates energy, but it's good because it allows us to roll, jump, turn, and stop. All right, now let's go ahead and look at the other one. Keep your eye on the red arrow. So your kinetic friction is what your friction after moving. That's going to be lower than your static friction, which is your friction to overcome the object in order to move. Okay. The board. I don't know why it cuts off. So he moved the board on one side and discovered, I think it was 23 newtons. Now, when he put the board on the other side, how many newtons do you need? Do you need more force, less force, or be the same? So the coil force, what do you think? It'll be more, less, or the same, or you can't tell? Go ahead and think about your answer. So whatever the area is, doesn't matter the area of the contact, it's going to be the same force, whether it's on the side, whether it's upside down, whether it's on the other side. So forces of sliding friction is much less than the force of static friction. Now the friction between two solids does not depend on the surface area in contact. Whether you put on the side or upside down, it's going to be the same thing. Friction now can happen even between surfaces that are not solid. For example, friction can happen between liquids or gases. Now let's look at the different friction with the different materials. So it definitely has the least friction, followed by your wood, followed by your sandpaper, and then your rubber is like glue. All right, now let me just come back over here. Now, when we saw the body, let's say the wood, the piece of wood. So we got, I don't know, let me just get around for the piece of wood. So you got the piece of wood right over here. This piece of wood is gonna have two forces. You're gonna have your gravitational force and you got your normal force. Now, when it accelerates, let's say it accelerates this way, we put a force on it that way, you're gonna have a frictional force going on the opposite side, and overcoming that, that should get your acceleration, and then your acceleration becomes, that's on your static friction, and then, static, you get the acceleration, and then when kinetic friction, you get, let me just write this down, either A or either B is gonna go. Now, this force, the frictional forces, the frictional force is gonna equal something called mu of S F of N. Or basically, well, let me just say force, so I won't confuse you. Let me go ahead and label these. Frictional force. Now your mu, that's going to be called the coefficient of static friction. And F, that's your force or normal force. Which again equals your A, your mass times acceleration. Now, we go ahead on this. So, frictional forces are essential for picking things up, walking, biking, driving anywhere, riding in a pencil, building with nails, weaving cloth. But overcoming friction force is also important because you got efficiency energies. Anything that we want to remain in motion, you're gonna have to overcome frictional forces. Now, there's two types of friction. There's the static again friction and kinetic friction. Static friction, the opposing force will prevent an object from moving. Now, you can have any magnitude from 0 Newton up to a maximum. Once the maximum is reached, forces are no longer in equilibrium and the object slides. When you had the video with the board, it took more force to move that board, and that's your static friction. Now, once you move, the force went down, that's what we're we're talking about kinetic frictional force, which is the opposing force that acts on an object and the motion has only one value, and generally it keeps on going. So it's actually smaller than your static friction. Now, properties of friction: if the body does not move, then the applied force of frictional force is balanced along the direction parallel to the surface, which equals in magnitude and opposite in direction. Now, the magnitude of the frictional force has a maximum given by mu F. Mu, that's called the coefficient of static friction. F is your force, which is your mass times your acceleration. So once you actually slide the board, the frictional force is decreased by Fk, given again your kinetic friction equals your coefficient of kinetic friction times your Fn. Let me actually go ahead and write that down. So static, let me go ahead, static, and then you got your and again, let me actually get a different color for that. This one is your kinetic friction force. The mu, that's your coefficient. Of kinetic friction. And again, that's your force, which is your mass times your acceleration. So the coefficient of kinetic friction does not depend on velocity. Okay. And they are static friction, scalar friction, and they should be scalar. Now, a fluid is anything that can flow. You were talking about either gas or either liquid. When there's a lot of body velocity between fluid and object, there's something called a drag force. Now, the drag force opposes the relative motion and points along the direction of the flow relative to the body. Now, your drag force will equal to, let me go ahead back to my little thing. So your drag force is going to equal to 1/2 something called C rho A V squared. Now, D, let me just go this is your drag force. You see this called your drag coefficient. Now, your rho, that's your density, which is your mass per volume, or mu squared, m over A, that's your area, cross-sectional area, and V is your velocity. So your drag force would be 1/2 C rho AB, and again, your C, that's called your drag coefficient. Your rho is your density, which is your mass per volume. Your A, that's your cross-sectional area, and your V, that's your relative velocity. Now, the drag force from the air opposes the falling object. So, go ahead and write this down. So, the drag force from the air opposes a falling object. Where your drag force minus your gravitational force is going to equal to ma. Now let's say the drag force is going to equal to your gravitational force. Basically, what we're saying is your 1/2 C rho A B squared is going to equal to your gravitational force, which is again your mass times gravity. It means solving this for the velocity, what you're going to have? You're going to have 2 multiplied by the gravitational force divided by C rho A, and then you get the square, so we square root this side. And this is what we call your terminal speed. So let's say we have an example, range of radius is 1.5 millimeter. Falls on a cloud, 1,200 meters above the ground. The drag coefficient for the drop is 0.6. The density of the water is 1,000 kilograms per meter cube. And the air density is 1.2 kilogram per meter cube. What is the terminal speed? All right. So let me go right ahead with this example. So let's see what we have. So you get your radius R, which is 1.5 millimeters, and it is 1,200 meters above the ground. All right. So your height is 1,200 meters, where the drag coefficient C is 0.6, and the density of the water was 1,000 and 1.2 for the air. Grams per meter cube, and density for the air, I'm going to call it EA, is 1.2 kilograms per meter cube. And we are trying to find the terminal speed. So we get our information, what we're looking for. Now let's go ahead and write down what the terminal speed is. So we know that the terminal speed, we just derived a while ago, is going to equal the square root of 2 multiplied by the gravitational force over C, your thermal speed in the air, because you're going to be following the air, multiplied by your area. Well, okay, so we got everything except for, well, we don't have the area, we don't have the gravitational force. So let's go ahead and figure out what is the gravitational force, Fg. So let me go right ahead. We need to find down Fg. So your gravitational force, which is going to equal to your mass multiplied by your gravity. But we do not have the mass. So we don't have the mass, but we know, let me go ahead and get a different color, that from earlier, your rho equals your mass per volume. Your density is mass per volume. That means your mass really is your density multiplied by your volume. So let's go ahead and do that. So substituting this, what you're gonna have, your gravitational force is gonna equal to, let me go ahead and label these out. Gravitational force, mass, volume, density. So this would be your volume multiplied by your density of the water multiplied by your gravity. Well, this is all fine and dandy, but we still don't have the volume. So your volume for a sphere we're dealing with a sphere, so your volume of sphere, which is going to equal to 4/3 pi r cubed, which r is the radius, which we already have. It's 1.5 millimeter. So really, our gravitational force was going to equal to 4/3 pi r cubed multiplied by the density of the water multiplied by gravity. Now, that's the first one we need. We also need the area, which the area, let me go ahead and get a different color. Let me go ahead. So we need the area. Now, your area, that's going to equal to your pi r squared. So let's go ahead and substitute everything in there. So let me go back to black. So we said that v, the terminal velocity, is going to equal the square root 2fg over c rho a multiplied by a. Now this is going to equal to square root, let me make this big. 2 multiplied by 4 should be 8. Should be 8 over 3 pi r cubed rho for the water, that's the water multiplied by the gravity, divided by the coefficient drag multiplied by your rho for the air multiplied by your area, which is your pi r squared. Well, what a coincidence. Our pi's cancel out. And then one of these go cancel out with that one. Two of these cancel out. So really what we're talking about is your terminal velocity is going to equal to your square root of 8 rho multiplied by r multiplied by g divided by 3. Actually, let me go ahead and rewrite it better than that. This needs to be a little bit bigger. And that's better. 8r rho w g divided by 3c rho a which, let's go ahead and substitute the numbers. So it'd be 8 times your 1.5 millimeters. So we needed meters, so it'd be 10 times 3. Let me go ahead and write this down on top. 1.5 times 10 negative 3 meters. Multiplied by the density of the water, which is 1,000. Multiplied by the gravity, which is 9.8. Divide all that by 3, multiplied by 0.6, multiplied by your air density, which is 1.2. So you should get I got 7.4, almost 7.4 meters per second. And this is exactly what we got. Now, let's go ahead and talk about centripetal force. We talked about that in chapter 2 a little bit, but we're going to be talking about it a little bit again. So centripetal force is an inward force that exerts on the object to keep it moving in a circle, in a curved path. Now, centripetal force is going to equal to mv squared over r. So, your centripetal force is mv squared over r. R, that's your radius. B, that's your velocity. And M, that's your mass. Now, actually, so let's say if you got an object, let's go in a real ugly circle. Let's say you got a circle here. Let's get an object that's going in a circle. So you're going to have an inward force. That's your force C, and this is going to control your velocity V. Let's say the object over here is going to be towards the middle, FC, where the object, your velocity is going to be this way. And so forth. Let's say this is over here, so this is going to be your FC, and your velocity will be headed towards over here. So the greater the object's mass, the greater the centripetal force. Now, the faster the object moves, the greater the centripetal force. The smaller the circle of the object, the greater the centripetal force. So let's say you have a 1,000-kilogram car. Let's say you have a 1,000-kilogram car traveling at 5 meters per second. That makes a 30-meter turn. How much centripetal force does it need? All right, so let's go back ahead. Here's your example. Now, your mass is 1,000 kilograms. And you're traveling at 5 meters per second. And your radius is 30 meters, and you're looking for your centripetal force. Okay, centripetal force is mv squared over r. So this is going to equal your 1,000 multiplied by your 5 squared, which is going to be 25. Divide that by your 30. And so what do we get? 100 divided by 330, that's 25. So we should get 833 newtons, which that's what we got. Let's do another question. Let's say the road hump has 12 meters in radius. What is the minimum speed where the car will leave the road on top of the bump? So you got a 12-meter radius, and you need the speed. So this is the other example. So you get your radius is 12 meters, and you want to find the speed. Now, your force is equal to force, so your gravitational force has to equal to your centrifugal force. Your gravitational force is mass times gravity equals your mv squared over r. So your masses cancel out. So that means your v squared over r is going to equal to g. That means your speed is going to equal to the square root of rg, which is going to equal to the square root of your 12 times 9.8. So that's 120, square root of 120 on one side. So it should be around 10.8 meters per second. Now, the uniform circle motion. Uniform circle motion is the motion of an object traveling at a constant speed in a circular path. Now, your velocity in this case will be your 2 pi r over t. So let's say we have a question. A wheel of a car has a radius of 0.29 meters, rotated at 830 revolutions per minute. That means rounds per minute. So you flip it to find how many minutes per round. So, all right, so you got 830 revolution per minute. That means it's going to equal to 1.2 times 10 negative 3 minutes per revolution, which is basically you flipping it. So it'd be this 1 over 830 revolutions per minute, basically. And we also have the radius, which is how much? 0.29. So your radius is 0.29 meters, and you're looking for your velocity. And again, we said the circular velocity is going to be 2 pi r over t. Now, so it'd be 2 pi multiplied by r, which is 0.29, but we don't have the time, t. Well, we said t was every circle revolution is 1.2 times 10 negative 3 minutes. So this little fellow over here, that's our time, which is 1.2 times 10 negative 3 minutes, which if we divide it by, or multiply it by 1 minute is 60 seconds. So we should get 0.072 seconds. So our time is 0.072 seconds, which we should get 25 meters per second. Wonderful. So when we're talking about when you're actually going in a circle again, right? So let's say this is your central circle. Let's say you're at this point over here. So you go from this point to this point. Well, you got an angle, let's call it theta. And this is actually, if you drop the line, what you're gonna have? You're gonna have a line over here, and you're gonna have a line perpendicular to this one. So this is gonna call alpha, and this is called beta. All the way down where it is actually, call three of them. So this is gonna be your 90 degrees over here. So alpha plus theta is gonna equal to 90 degrees. Right? Again, that's the object moving. Well, if this is the case, we also have a 90-degree angle over here. So that means your alpha plus beta is also going to equal to 90 degrees. That means if you actually subtract both of these, what you're going to have? Alpha minus beta is going to equal to 0. That means your alpha is going to equal to beta. So if you take that line, basically you got, here's just the C over here, and this is your curved path. That's your radius. Now this is going to be your distance. You remember your velocity is distance over time, which is your d over t. That means your distance is your velocity multiplied by your t. So this one, these two will be your radius. This one will be v, and your change of time, delta t. Meanwhile, if you compare with a triangle that you actually deal with the velocity, so let's say this is your velocity, v at the initial, and this is your velocity at t final. So this is going to be, again, your change in velocity. So using the law of triangles on both of these, your delta, for the first one, your change in velocity over your v, let's say on this one's going to equal your v delta t over your r. That means your delta v over delta t is going to equal to v squared over r. Which, remember, your velocity over r, that's actually going to be your velocity over time, that's going to be your acceleration. So in particular, your centripetal acceleration is going to equal to v squared over r. So let's say if we have equation, bobsled track contains turns of radius 33 and 24 meters. Find the centripetal acceleration at each turn for a speed of 34 meters per second. So in this case, you get two of them. I'm going to call them 1 and 2. example. So R1 is 33 meters and R2 is 24 meters. They both have the same speed, which is 34 meters per second. And this one is 34 meters per second. You want to find the acceleration for this for one and the acceleration, centripetal acceleration for number two. So AC for this one, again, is going to equal to V squared over R, which is going to equal to your 34 squared over 33. And this one, AC1. AC2 is going to equal to your 34 squared. Let me start that equation. V squared over R, which is going to equal to your 34 squared divided by your 24. So for the first one, we should get 35 meters per second squared. For the second one, we should get 48 meters per second squared. $35, 48, and again, 35 is 3.6 gravity, 48 is 4.9 G. So, now we said the centripetal acceleration is V squared over R. We actually derived that a little while ago. Now, your force is your mass times acceleration. So your centripetal force, your mass times your centripetal acceleration, which equals to your mv squared over R. So, and that's how we actually got your centripetal force to equal to mv squared over R. And that should conclude chapter 6 for Physics 101. If you have any questions, go ahead and email me. You can give me a call at 256-348-1480. Thank you.